So we'd like to welcome you from Intel Software Group to debate our Spark Beta being hosted at Intel. It gives me, actually, we have a surprise today. It gives me real pleasure to, if my laptop will start working. So something is not right here. So our Vice President, Michael Green, he's the Vice President of the Software Services Group, and he's General Manager of the System Technology and Optimization Division within the Software Services Group. And he's the sponsor of all the big data software analytics that happen within Intel Corporation. So he really, took, time off his busy schedule just wants to come back, come here, say a few minutes, a few couple words to welcome everyone. Michael?
Came here for a pizza, but I was late. So, thank you for coming. There's always so much talk about big data, but really what's exciting for me is really to welcome you, because you guys are the magicians. We have all this work, the data lake, but we're looking to you around machine learning, analytics, to find all the hidden jewels that are hidden in the data lake. And today, as we'll go through more and quickly go into the technical part from machine learning, without you, it's just not going to be possible. Of course, we're at Intel. We're famous for our silicon, but really our silicon is just the start. What that serves as a platform for is all the analytics that you'll be doing to identify the business intelligence above it. Yesterday at the IDF, there was an interesting conversation around cancer research. So much work going on and trying to understand what we can do to really identify and personalize medicine. And all of that, as we start to talk about the conversation, which was really interesting at the Intel Developers Forum, being known so much for our silicon, most of the conversation was about software, whether it was talking about robotics and how we're controlling the software there, whether we're talking about cancer research and the software and analytics and algorithms, machine learning that's required to turn that into personalized information. We talked about different analytics platforms. Over and over again throughout the 3 days, software was the focus. So with that in mind, I'm excited to see the software developers here. Looking forward to having you participate and really bringing forth your talents and competencies to truly help change the world for the better. So with that, I'd like to introduce okay, and with that, I will pass it back. You wonder who works for whom someday? Sure. Famous last word. Let me just leave with one thing. So I'll skip the part with Jason. I'll let Fadi take care of that. But really, thank you for all the people at Intel, as well as the partnership that we have with Databricks as well, to help set this up so that we can pull that together. Really appreciate your participation, but also working. I saw people flying out of here to go pick up coffee, so as well. It takes a lot of groundwork was really done just out of passion, and just very proud of all the people who helped pull this together. All right, and with that, I'll pass it off to Fadi.
Thank you so much. Thank you, Mike. Just I wanted to make sure to put the plug for the Women in Big Data Forum. Fresh instruction came. This got kicked off at the Intel Developer Forum. I wanted to make sure your female colleague, all the women in the audience, there is industry-wide new forum started around big data and women technology. Encourage you to join that, pass the word along. We'd like to grow that group. That's the reason I wanted to make sure to put that plug.
Good reason.
And with that, we would like to welcome our speaker, Jason Dye. Jason is currently the Chief Architect for Big Data Technology at Intel. He was principal architect in Microsoft prior to joining Intel. I'll let you read the great accomplishment, but really what I want to highlight is he's a PMC member at the Apache Spark project and has published over 15 technical papers, filed over 20 patents, and taught several computer classes at multiple universities. So with that, I'll let Jason go on. This mic too, or you have two mic already?
I already have two mic.
Only once, okay, perfect.
Yeah, it's okay.
Right.
Yeah. Yeah. Okay. Yeah. Thank you everyone for joining today. Today I'm going to talk about our work on building very large-scale distributed machine learning on Apache Spark with many of our partners and users. So, first, some background. We all know that the Apache Spark project started as a research and open source project from the MP Lab in UC Berkeley. Actually, they have an awesome analytics stack, the badass, as they call it. And Intel actually has been working very closely with MP Lab since the early days. We started to work on Spark since 2012, when it is still a research project in the lab. And we work with MP Lab as well as many guys in the open source community on the development of the project and contribute many key features in the project. In addition to that, we actually have also been working with MP Lab very closely on many of other components in the badass stack. I mean, Tachyon, Spark we are actually a major contributor, major on those projects too. In addition, Intel has also been working with many of our customers, users, partners. So most of them are those web scale companies like Tencent, like PayPal, like Alibaba, and so on. We have been working with them to build the advanced analytics applications and systems on top of Spark, including real-time stream processing, very low latency interactive queries, as well as the very large scale distributed machine learning and graph analytics. So today, I talk about our efforts in building those large scale distributed machine learning on Spark, including the implementation of many of those advanced algorithms, as well as some of the infrastructure work we have been working on, especially our initial work around the parameter server for Spark. Okay, first, let's look at some of the algorithms. First one is actually a sparse logistic regression we have been working on for a while. This is essentially this is how a logistic regression is implemented in Spark today. And typically, whether it's a version in MLlib or there is different variations people have built for their applications, this is how it is actually structured. So it's a giant loop, and in each iteration, the driver will broadcast the weight, the W, to every worker. The worker will actually perform to compute the gradient for that mini batch. So assume you have B records you need to go through in that mini batch. The driver, so each task running on the worker will actually get a random sample of the data, which is partitioned across all the worker nodes. Sample the records, compute the local gradient, something like that. And then after each task on the worker side compute its local gradient, it will then send the local gradient back, have it aggregated. Typically, it's averaged. And you can do it using a reduce. Or if they're at very large scale, you may want to do it using a tree aggregation. But in any case, the gradient are aggregated from many different local gradients and into a global one, and the driver then updates the weight using this type of formula. So this is how it works, typically. And the problem is that we actually have a pretty large problem set things. For instance, for our model size, we actually have, we are working with a lot of the partners who actually have hundreds of millions, or even sometimes billions, several billions of unique features. So to get that in perspective, I mean, for the weight and the gradient we just talked about on this page, they're actually a double vector. And in that vector, there will be an entry for every unique feature. So let's say you have 100 million unique features, which means the driver needs to broadcast W, which you have which is a double vector with 100 million entry, which is 100 million entry of double is 800 megabytes. I mean, if it's a billion, you can do the math. So you need to broadcast it over the network to the workers, which is a huge network. And then each task needs to compute a G. Again, the G is a double vector with 100 million double. So it's, again, at least 800 megabytes, and it could be much larger. And then aggregation, again, the same thing. So there is a lot of pressure on the network in that the driver needs to send the weight across the network, each task on the worker will compute its local gradient, which is, again, 800 megabytes object, send over the network, get aggregated, and so on. In addition, all the data, all the training data we have, you could contain billions, sometimes even trillions of training samples. And the zero data are typically partitioned across the worker and cached in memory. So that's a large memory pressure as well. So those are essentially the network and memory bottleneck actually our user encountered in the application. In a lot of cases, they have to actually, instead of running the complete model, they have to actually filter the parameters, they only be able to run a subset of the model. So, well, there is a few optimizations actually can be applied when you're actually building this type of applications. In particular, real-world data are extremely sparse. For instance, we're working with some of our users on their click log data, click-through data, and they have, say, 100 million of unique features. But each sample in their log, essentially, if you think of each sample as a low, they have hundreds of millions of fields. But among those fields, most of them are actually zero. The non-zero elements is typically several hundred, or maybe about 1,000. So the data is extremely sparse. So first of all, you can use actually sparse vector for all the gradient. I mean, if you look at this formula here, I mean, the gradient is computed using this one, and the first element is a scalar, and the second element, xi, is the sample, and which is, again, a vector. But as you can see, if the element in that xi is 0, the corresponding element in gt is also 0. So gt is actually very sparse. So you can use a sparse vector to represent the g. And also for the training data, you need to cache it in the memory. And this also, so this has a lot of memory pressure. And again, you can switch to a sparse format. And in addition, typically people just use the double, for instance, to use double to store all the data. But in reality, actually, this can be further optimized. For instance, a lot of most of the application we have, they actually don't need a double. Floater will do just fine for those guys. And a lot of data actually are binary data. They are not actual. They don't have actually double or float values. They have just either 0 or 1. So in those cases, you can just build a binary, a format for optimizer for the binary data. And with all those optimizations for data sparsity, we actually help our customers, help our users to actually improve the scalability by 10x. So essentially, previously they only run the model in maybe several million, or maybe 10 million, and then they can scale to say hundreds of millions of unique features. At the same time, actually improve the performance by about 4x. So that's some of the improvement we can actually get by leveraging the data sparsity in the real world training. Well, in addition to those memory and network bottlenecks, Then another type of overhead we actually have been looking at, which is related to distributed training. So we try to understand what are the overhead which is brought by the distributed training. So we structure our applications in the form that, as you can see on the right side. So as I mentioned before, this application is essentially a giant loop. So each iteration is essentially a Spark job. So in each iteration, I launch a Spark job. And in that Spark job, it first broadcasts on the driver, and then it runs tasks on each different worker. We structure the program in that it only runs one batch of the task. So all the tasks are launched at the beginning of the job. And then when the task finished, we do a simple reduce to get all the gradient from each task and get it aggregated and then updated on the driver. So we try to understand what are the overhead, which essentially is the network communication, the synchronization, the aggregation, essentially everything that is needed outside the computation of the task. So if you, so this is how we compute the overhead. The average Spark job running time is essentially the average job running time for each iteration. And the average task running time is the period where actually the task need to go through all the sampled training data and compute the local gradient. And as you can see here, actually, if you have a smaller mini-batch size, this is a mini-batch size across all the workers. So if you have smaller mini-batch size, you can actually, most of the time is spent on the driver, on the network, on the synchronization, or so on. The task actually, the computation time spent on the task, which actually scans through the data, compute the local gradient, is actually very small. On the other hand, you cannot solve the problem by just using very large batch size, because in practice, the converging speed, the time it takes to actually converge into a particular error rate or loss value actually slow down significantly when you have a very large mini-batch size. So in this case, in this particular example, try to converge it to a loss value of 0.59, you actually need to use mini-batch size of about 160K. So essentially, this corresponds to the third dot here. So you still have pretty high overhead related to distributed training, but you get a reasonable convergence of speed. So what we can do to improve? So there are a few things we think a permitted server type of support is actually important. First of all, it can help you to leverage the data sparsity further. In our current implementation, the driver still need to broadcast a weight, the full weight, to each worker. But in reality, I mean, all the tasks in the worker only need a subset of the entries in the weight. So you do not need actually to broadcast the full set of the weight to the worker. And the secondary is related to this distributed training overhead, in that a lot of them actually is really due to we are using a kind of a BSP model in Spark when you do all the training. And so you need to actually synchronize and aggregate and wait at the end of the job for the other tasks to finish. So maybe it's possible to actually to introduce the weakly synchronous models using a permitted server type of architecture. And finally, yeah, you instead of doing the aggregations and the update on a driver, which is a single node, you can do it in a distributed fashion. Okay, this is the first piece of the algorithm. And the next one I would like to talk about is the distributed topic modeling, especially LDA type of algorithm we have been building with many of our users. Well, topic modeling is essentially, in topic modeling, you are giving a set of documents. And the algorithm tries to automatically discover the topics discussed in those set of documents. So only the documents are observed. No topics actually are given, and you need to infer that automatically. And well, I don't want to go through all the details of those mathematics here. So if you're interested, you can refer to this paper. But the latent district allocation is essentially the algorithm of choice we actually use to build a lot of those topic modeling applications. So we have been working with many of our users and partners on large-scale topic modeling on Spark. They're actually used in many different applications, such as ad selection, news clustering, some of recommendations, and so on. And they have different applications actually have different problem setting. In the first one, you have about 300K words and 4 million documents, and about 10,000 topics, which is actually reasonable. But there is cases you have very large number of topics. Say in one case you have 1 to 2 million topics you try to infer. And in another case you have actually 3.3 billion docs you try to process. And we actually have built a package of different topic modeling algorithms, and we actually have shared it with the community. The code is available on GitHub, and it's also some discussion in the Spark Jira. And the package actually contains a set of different algorithms, including online LDA. An earlier version of that is actually get merged into MLlib 1.4. And GIP sampling LDA, which is actually adapted from some of the PR and the Jiras from the community. And also we have a implementation of online hierarchical LDA, which is based on the paper. Let's look at the online LDA. The online LDA, it's already, as mentioned, it's already in Spark. It's released as part of Spark 1.4. And this is how it works. So in the first step, the driver will broadcast a matrix, which essentially is a word topic distribution. So it has it has one row for each topic and one column for each word. And this matrix is then broadcasted to every task running on the worker. Each task running on the worker will then sample a subset of the documents which is distributed across all the workers. Compute a new status matrix, again, topic multiplied by word. This is how it's large, and then it gets aggregated and updated on the driver side. So what are the problems? What are the benefits? What are the problems with this approach? So the benefit of that is actually this algorithm actually only needs to process a subset of the document in each iteration. So in many of the GIP sampling-based processing, you actually need to go through all the documents in every iteration. This one actually helps when you have a very large corpus of documents. And also, it is possible for you to actually adding new documents to your corpus. When you just stream in new documents into the system, and it gets processed naturally. The problem with this approach is that, there is actually a pretty large memory or network pressure when the topic number or the word number is very large. Because, as you can see, we need to broadcast a matrix. And this matrix is a double matrix, and it's a dense matrix. So most of the elements in that matrix actually is non-zero. And in that case, if you have very large number of topics or very large number of words, it could become a bottleneck. The other alternative algorithm we have built is actually based on GIP sampling. In that algorithm, the model is actually structured as a graph, a bipartite graph. So the source ID is actually all the words, all the different words appeared in the document. And the destination ID is actually the document ID. So every edge represents that word actually appears in that document. And a word can appear actually multiple times in one document. So on the excuse me, for the attribute of that edge, it actually contains the topic assignment for each token, which is one appearance of the word in the document. So, for instance, let's look at word 1. It appeared in document 1, and it appeared twice. And in the first time when it appeared, we assign a topic T1 to that appearance. And for the second appearance, we assign a topic ID T2. So this is essentially how all the edges are actually organized. And on the vector side, on the vertex side, it actually contains a vector size of topics. So for each entry in that vector, it shows how many times that particular word or that particular document has been assigned to that that topic has that topic actually appears in that document, or that word is assigned to that topic. So it's essentially a word topic assignment counter for the word or document topic assignment counter. So it's a vector. It's an int vector actually, and it contains how many times that topic is assigned to that word or document. So this is how. So essentially, we're building a graph-based analysis algorithm for those keep sampling-based LDA. And with that graph, the implementation is at a high level. It's a giant loop, and the inside loop you first sample doing the sample tokens, which is essentially using the map triplets API in GraphX, which processes each edge and assign a new topic to the token. And it's based on some of the keep sampling, using the keep sampling mechanism. After every token, which is every entry in those green vectors, is updated, it will run a aggregated update counter method, which is essentially a aggregate message compute operation in GraphX, which will compute the counter other counters on the vectors. As you can see, for every word, for instance, for word for word 1, it has 2 assignments of topic 1 and 1 assignment of topic 2. If you look at both those 2 edges, so based on those edge values, I can compute its vertex value by using those edge values, and we can do the same for every vertex, whether it's a word or document. Well, this is how it is structured. But the next question is about what are the performance and the scalability bottleneck in this application. So, if you are familiar with GraphX, there is in GraphX there is a vertex and there is edge, and both vertex and edge are actually RDDs in Spark, and the vertex are partitioned and the other edges are partitioned, and the vertex has its attributes and the edge has its attributes. And when you try to do those processing, for instance, doing map triplets, you actually need to construct a triplet RDD, something like that, which is kind of a materialized view in that you get those edge RDD, and then you shuffle all those vertex, the attributes of that vertex to the corresponding edge RDD or edge partition. So in this case, the attribute of vertex A need to send to the edge partition 1, and the attribute of vertex B need to send to both partition 1 and the partition 2 because it appears both in partition 1 and partition 2, and so on. So it actually involves a lot of network shuffle, which is one bottleneck we actually have observed when you try to replicating those vertex to where its adjacent edge is located in those edge partitions. And we actually use a simple, say, Wikipedia dump to test. And on 8-node server, it actually involves about 186 gigabytes you need to actually shuffle around the network, which is actually a pretty large data you need to shuffle around. And in addition, you need to cache those edge RDDs or triplet RDDs in memory, because when you do a compute, you want to actually compute in memory. And the cache those edge ID, cache those triplets actually consumes a lot of memory too. So in our example, we actually use about 380 gigabytes on each node. In addition to caching those triplets, in every iteration you will do a map triplet, which will generate a new set of triplets. And when you generate a new set of triplets, you actually will generate new data. So that's actually a lot of pressure on the memory as well. So that's actually the first bottleneck we have actually encountered. And well, here's how we actually optimize some of the optimization we can apply for those applications. First of all, again, there are a lot of data sparsity. For every vertex attribute, whether it's a word topic assignment or doc topic assignment, they're actually pretty sparse. For each document, for instance, each document is actually maybe 200 words or 300 words. So even if you assign a different topic for every word in that document, you won't have every topic actually appear in its topic assignment. And even for the word topic assignment, it's actually pretty sparse too. So if you think the other vertex attributes as a matrix, every column is a topic, every row is a vertex, whether it's document or word, it's pretty sparse. About less than 15% of them is actually missing. Less than 15% of them actually exists. So all the others are missing. And when you actually close to the convergence, actually only about 5% is actually has a value, and all the others are missing. So a natural way actually to implement it is to use a sparse vector for all the vertex attributes. However, on the other hand, as we found out, after replication, we see actually, so a lot of those vertex with dense attributes actually get replicated much more times than those vertex with a very sparse matrix. Because, well, this is actually pretty intuitive in that, I mean, vertex with a lot of, with a dense attribute actually tend to have a lot of edges. So it ends up with, will appear in a lot of edge partitions, and at the end of the day, you will need to replicate it a lot more times. And in that case, it's actually using sparse vector for dense data is actually pretty bad, because you need to, I mean, for sparse vector, you need to store both the value and the index. And if you have if every index has a value, you actually need to end up store twice as more data. So what we try to do there, so instead of using a sparse vector, we will dynamically generate a attribute based on its value. And if it's a dense vector, we will actually generate a dense vector. Otherwise, we generate a sparse vector. So that's the first optimization we have done. We try to look into the state sparsity. And the second one is really about the partitioning. As I mentioned before, all the edges need to partition across the network, and every vector needs to replicate to the edge partition that it appears. So there is several generic partition strategies we have tried. Some are degree-based, some are hybrid, and so on. All those actually generic approaches try to balance the data. So try to make sure that the edge when edge partitions are actually balanced across all the different workers. However, it does not care about, or does not try to optimize the replication factor of vectors. And so what we end up doing is pretty simple. One observation we have is that actually for the documents, most of the documents are pretty small. I mean, a document is about 200 words or 300 words in most cases. On the other hand, a word can appear in many different documents. So what we try to do is we just partition the edge based on its destination ID, which is the documentation ID, doc ID, which essentially means all the edge related to a document we will put it in one. We'll keep it in one partition. Since the document is pretty small, there is no data skew. And at the same time, you do not need to actually shuffle or replicate all those document, those vectors for documents. So the result is that after those optimizations, we get about 3x reduction in the data we shuffle. It's from 180 to about 60 gigabytes. At the same time, the running time is reduced by about 1.67x. So that's the network shuffle side. Then the next question is about the memory. We still need to cache a lot of memory even after all those optimizations. I mean, we run one example which has about 48 million documents, 500 keywords, and it had about 800 million edges and 1.2 tokens. A token is the appearance of a word in one document. So the Vertex RDD is cached. We have about 512 Vertex RD partitions, and for each partition, it has about 10K vertex and about 10 megabytes memory. However, if you look at the edge partition, we have 512 in total. However, for each partition, it has about 1.1 million edges and about 100K unique vertex, which is all the vertex that appear in those edges. And then it uses about 750 megabytes to cache each edge partition. And among those edge partitions, among those memory, about 560 megabytes are actually used to cache those replicated vertex attributes. So it's a simple math. So every vertex needs to replicate about 10 times across the edge partitions. And for the attribute, if you count in the memory, it's 56x. Which is actually, at the end of the day, the replicated vertex attributes turn out to be a huge scalability bottleneck for those applications running on GraphX. That's one part of the problem. The other part of the problem is, RDD transformation actually also needs a lot of memory because in Spark, RDD is supposed to be an immutable distributed data set. So how do you get a new data, a new RDD? You do it through some coarse-grained transformation. So you get a RDD R1 and then generate a new set of data, which is R2, and so on. And in particular, in our sample token, the sample token operations in keep sampling LDA, as I mentioned, it uses a GraphX, the map triplet in GraphX, and which is essentially a map partition on the edge RDD. And in that operation, for each triplet is essentially an edge with the source and destination attributes. And for each token, which is, as you remember, each edge contains a vector, and each entry in that vector is a token here. So for each token, we need to assign a new topics through some sampling. And then after that, I will need to update the word topic attribute and the doc topic attribute based on that new assignment. And finally, I generate a new edge attribute. So this operation, as I mentioned, as just talked about, in the first step, we assign a new topic to that token. After we assign a new topic, I need to update that counter, which essentially I will decrease the old topic counter by 1 and increase the new topic counter by 1. So in that case, I will keep the counter correct, which will be used in the sampling process. You can, if you really try to maintain the semantics of RDD, you really need to generate a new copy of those vertex attributes, and then you operate on that. But that actually involves a lot of memory. As we just talked about, the vertex attributes use about more than 500 megabytes. And if you want to generate a new copy of that, that's 500 megabytes you need to generate. Or you can just directly update the attributes in place, which is efficient in terms of memory usage. On the other hand, the RDD is no longer immutable. So it could be potentially it could lead to incorrect behavior. For instance, if you have that RDD cached, and then you try to do that sampling, you update its cached vertex attribute, and then something goes wrong in that task, you try to rerun the task again. The previous data is already modified in the middle, and you're not going back to that previous data, which actually lead to incorrect behavior. And also, if you have a speculative execution, you're getting 2 threads updated the vertex at the same time, which is bad. So this is how the chain of the transformation actually looks like. This is not a this is not 100% accurate RDD chain or RDD lineage, but it actually gives some illustration of how those transformation works. So in that iteration, you start with the edge, say edge I. You're doing a sample token, which you get a new edge I prime. And then based on edge I prime, you do a update counter, which essentially aggregate message. You get a new vertex, vertex I plus 1. And with that, you will shuffle the data, shuffle the attribute in those vertex I plus 1 to the edge partition. You generate edge I plus 1, and then you just iterate. So the blue box are what get cached, and the blue arrow actually shows you need a shuffle, network shuffle to you need a network shuffle actually to aggregate all the data, aggregate all the messages to compute a new vertex, and then represent vertex to every edge. And for a lot of those edges, you will have the replicated vertex attribute by replicating all the data from vertex to each edge partition. And as you can see, if we in the sample token, we can do in-place update on those replicated vertex attribute. Well, it is efficient, but it can go wrong if you have failures and so on in your computation. When you try to rerun the task, you end up with a modified data, and you cannot go back to the previous state. So what we end up doing is actually we actually try to address both problems: the caching of the RDD, very large memory used in caching, as well as the in-place update support, through some very careful management of the cached RDD state. So what we try to do is, say, if we can actually start with a cached vertex and the cached edge, and in that edge we do not actually maintain any vertex data. So that edge has no vertex attributes replicated. If we can start with that, and then when we do the in each iteration, we can do a shuffle to get the data from the vertex, get to the edge, and then we do a sample token on that edge I prime. We can do an in-place update on that. After that, we get a new edge. And then one step we added is actually we then remove all those replicated vertex attributes. We get an edge I plus 1, and then we cache it in memory. And then we can, using edge I plus 1, we can compute a vertex I plus 1, and then the compute iteration. And the iteration, actually, we can go to the next iteration. So the benefit of that is that, first of all, we no longer cache those replicated vertex attributes. Because among the about 750 megabytes used to cache those edge RDD, edge partitions, actually about more than 500 million megabytes is actually used to cache all those vertex attributes. And turn out we do not need to cache that. We can compute it from those vertex RDD through shuffle. And secondly, we do not we do the in-place update in sample tokens. And if anything goes wrong, if say I need to, if there a task failed, I need to rerun the task, it will actually go back to those cached data and do another shuffle and try to get the data. So you always get the previous data, unmodified data from the beginning. So in that case, we can actually solve both problems. And in that case, we solve the correctness problem, and at the same time, we reduce the memory usage by in caching those edge RDD by, I think it's reduced by about 3x. So next step, what we try to do is still, we try to, again, some of the parameter server type of architecture is useful because replication, I mentioned the replication of those vertex attributes is still a major bottleneck for in memory usage, in network shuffle. It's actually still a bottleneck in GraphX. So a lot of applications actually have this type of bottlenecks, and we are looking at, by using a parameter server type of architecture, we can keep one global copy of those vertex attributes, and then we can, first of all, no replication is needed. And secondly, we can actually leverage the data sparsity in those workers, because on each worker, it only contains a subset of those edge partitions, so it actually do not need all those vertex attributes. And yeah, of course, we can do the aggregation and the update. Instead of being shuffle, we can go through the parameter server in a distributed fashion. So that's a lot of, well, as I mentioned, we actually have building a lot of those distributed machine learning algorithms, and as we see it, it's actually, Spark actually provides a pretty nice framework for people to build this type of algorithm. However, to actually really support very large scale model, very large scale distribution, a lot of optimizations are still needed. And I'm not going to talk into detail about those algorithms. We actually have building a lot of those algorithms. Or maybe I just have one page for that. We have an initial implementation on the convolutional neural network on Spark. We tested on Minster, and we are working with the community, try to, in the current Spark, there is a very initial support for those artificial neural networks, the multi-layer perception, essentially multi-layer perception checked in. And we are working with the community to try to adapt to that framework, to adapt to that architecture. There are a lot of discussions happening in that Jira. But in any case, this is one particular example, the convolutional neural network, and also those factorization machines and so on. They all actually need very large model size, billions of unique features. That leads us to some of the initial work we have been doing is around the parameter server. We have been working with some of our very large users and customers who have very large model, billions of unique features, or maybe tens of billions of unique features to try to support. And we are doing some initial work to understand what are the best way to add this type of parameter server type of support for the distributed machine learning on Spark. Well, if you are not familiar with that, I mean, in concept, it's actually pretty simple. You have a separate parameter server, which is distributed across the network, across the cluster, which contains a global copy of all the parameters used in your machine learning algorithm. And the tasks distributed across the worker read the data, and then read the parameters from the global parameter server, do its local computation, and push update to the global parameter server, where it is aggregated, updated, and then you get a refresh of the parameters from that parameter server, and so on. So it allows us to actually build a very large-scale model of graph, billions or even tens of billions of unique features. It allows the parallel aggregation and update of those parameters. I mean, today, a lot of those aggregation, if you look at the logistic regression example, it's actually done on the driver, which is a single node. And also, there is with the parameter server, it's possible to actually introduce asynchronous into the distributed training. So instead of doing a BSP model of training, everyone needs to wait at the end of a iteration. It's possible you actually can inject some type of asynchronous into the training. So we are currently working with the communities. There is a Jira opened. Actually, we think it's at this stage it's actually probably important to define the right PS interface. What are the abstraction? What are the data model, and so on. For Spark first, which can be decoupled from the actual implementation in that I think probably people will need several different implementations to look at, but you probably want one right interface defined so that people can build different underlying implementations. So there is we have an initial proposal in that JIRA, and based on some of our previous work with our users. And so if you are interested, I encourage you to look into that JIRA and join that discussions. But a brief overview of that is essentially we think of the Permissive server is essentially a specialized NoSQL system with a specific support for distributed machine learning. So if we look at that Permissive server, there is you need to define the right data model, what operation you want to support, what are the synchronization model you want to support for those distributed training, and what are the fault tolerance you can support. And finally, how you're going to integrate with Spark and GraphX and so on. So, well, when we look at the Permissive server, we believe that beyond those conventional key value or maybe table store, we actually really need to support those linear algebra objects for those machine learning algorithms. For instance, the vector or matrix. I mean, for instance, all the gradient and the weight used in the logistic regression can be modeled as vector, and all those word topic distribution assignment in LDA or those weight bias in a multi-layer neural network that can be modeled as a matrix. So you will have this type of object CRUD interfaces to actually manage those vector and the matrix. And one particular important optimization we have actually used is that you need to have a better control of the location and partitioning of those parameters. For instance, some of the parameters really need to be co-partitioned on the same physical node for improved performance. For instance, the weight and the gradient in logistic regression, they really need to be co-partitioned, and so that when you try to do update, when you do an update, you essentially take the corresponding element in gradient and update the element in weight, and you can do that actually in a local. You're using a local computing if those two vectors are co-partitioned on the same physical node. So that's one particular important optimizing we think that is useful. So of course, there is a few other areas we try to investigate. For instance, it's probably important to actually add a flexible partitioning strategy. One particular example is we have a use case where it seems important if you can partition the parameters together with the data, which allows you to reduce the network communication and so on. And also, one particular question we actually try to answer is, in addition to the vector and the matrix, is it useful to actually support those more general multidimensional arrays? With the vector and the matrix support, we actually need two types of operations which are widely used in those machine learning algorithms. One is some form of aggregation, which essentially is additive aggregation operation, which can be performed by every task in parallel. So for instance, you try to sum, when you aggregate the gradient, you try to compute the sum of those other local gradients. Or when you try to do the aggregation of those word topic assignment, you try to do the sum of those new assignments. So there's some there is some add type. It's not necessarily add, but you need some commutative and associative computing aggregation operation you need to support. And then you need to update that parameters. Typically based on some synchronization criteria. For instance, in a BSP model, you will update the parameter after all the tasks are done, and then wait for all the tasks are done, and then you update the parameter at the end of that iteration. For now, it looks like an XPBY type of update is actually pretty useful for most of the application we look at, but there could be more general support needed. Okay, this is shows one example of how you can actually implement the Minibatches SGD using this type of operations. So there is a loop, a giant loop. In that loop, you actually look at the data. You compute every task, get a partition of the data, compute a local gradient. After you are done, you actually aggregate the local gradient using that aggregation add to vector operator. And after other tasks are done, at the end of that iteration, you will try to do a update by this formula. The gradient it will be weight multiplied by the linear rate and the regression parameter and then so on. Basically, this allows you to implement a very simple mini-batch SGD. There is, of course, some discussion around how we can actually support those flexible aggregation or update operations, maybe through some user-defined function type of interface. But this is some work or some discussion in progress. Well, the other important concept we need to support is around epoch, which represent some unit of progress made by the machine learning algorithm. In most cases, it's one iteration of training. And so we actually have a namespace architecture in that in the parameter server, we allow multiple machine learning applications multiple model training to access the same parameter server, so that we create a different namespace for them. So different application can actually create the parameter and the different namespace. And we associate an epoch with each namespace. So you can set an epoch or get an epoch for that particular namespace. So this is how a BSP type of training will look like. You will first create, so this, let's say this is a simple logistic regression. You will create a namespace, create a vector, and create a co-partition vector. And then in the training, in the iteration, you will just iterate. And in each iteration, you first set the epoch, and then you compute the local gradient doing the aggregation, and finally you doing the update at the end of iteration, and then you advance to the next epoch, which seems trivial for BS type of training. However, it actually will be pretty important if you try to support different synchronization models. For instance, if there is some proposals in the literature about just SSP, stale synchronous parallel, in that instead of asking every task in the same epoch to wait for each other, it allows different iterations actually to run parallel, in that there is upper bound of how far you can, if the fastest can go. Essentially means that the slowest task and the fastest task maybe is maybe 3 iterations away or 5 iterations away based on the setting. And in that case, actually, the epoch-based management is actually pretty important to support this type of asynchronous model. And also, it's actually pretty useful to support fault tolerance. By introducing the parameter server, it actually introduces new failure scenarios. For instance, what if a task is updating or aggregating a model and it failed in the middle? It actually completes the aggregation, but then it failed after aggregation. So there are different new types of failure models. A failure scenario can happen. And currently, we are just building a very coarse-grained fault tolerance scheme. Using the epoch, we're doing epoch-based checkpointing with the BSP model. So it's, well, as you can see, it's the same. It worked as before. You have iteration, and you're doing the training, and set an epoch, and doing the training, and you're doing update. And periodically, you will checkpoint the parameters associated with the current epoch. So in this case, say for every 10 iteration, you try to checkpoint the current parameter. And if anything goes wrong, whether it's in the driver or in the worker, you just reload the parameter you just checkpoint, and then you start from there again. This takes advantage of the fact in that for most of those machine learnings, you have immutable data. And you just, so if you can automatically checkpoint those parameters, actually it's easier to recover. However, we believe that there's some final grade fault tolerance is actually needed here because, first of all, a lot of those machine learning algorithms is kind of failure resilient. You can actually, you do not need to actually go through all the data. And the secondary, I mean, there is some asynchronous model we can support, which probably make it probably easier, not necessarily easier, but probably more efficient to recover. So yeah, that's what we are actually currently have been working on with some of our partners and users. At the same time, we have been working in the community, try to get the feedbacks to see what are the right interface we try to implement and what are the answers to the possible future works. In particular, how we want to integrate with Spark. For instance, one approach is probably we can run it as similar to how the shuffle service is running in Spark today. Run it as a say auxiliary service in the Yarn as a name node auxiliary service, something like that. And also, we I think one of the big motivations is that the replication of Vertex attributes in GraphX is a scalability bottleneck, and we are looking at to put all those Vertex attributes in parameter server so that we hopefully can scale better. Okay, I think that's pretty much what I want to cover today. So in summary, we see actually the Spark has become the framework of choice for a lot of people to build those advanced analytics and machine learning applications on the big data in a distributed scale-out fashion. There is already a lot of support inside Spark. At the same time, our team at Intel has actually been partnering with many of the web scale companies to build those distributed machine learning on Spark, including various algorithms from logistic regression to LDA and so on, as well as some infrastructure support such as the parameter server. And we have been working very actively with the open source community to bring our work to the open source, contributing our work to the open source, get it merged into Spark so that we can help improve the analytics capabilities on Spark. Well, that's it. Thanks.
Questions?
Yeah, if there are any questions.
Maybe use microphone. Maybe questions. I'll put the second microphone next to you because we're recording. Go ahead, speak.
Oh.
Yeah.
Hi, Jason. This is Vikram.
That's fine.
Vikram Salekar from Intel. So, we know that Spark has challenges in shuffling data. There are bottlenecks that are indicated as network. But in addition to that, I mean, in a sense, it comes down to network, but there are actually, the shuffle involves like writing to disk, and then doing a sort, doing off-heap sort, and then actually doing serialization, deserialization, and then network, right? Do you have any data as to what percentage each of some of these components are in some of the measurements that you how much is network contributes to overhead, and how much serialization, deserialization contributes to overhead, or how much, for example, to that?
Yeah, I think it actually depends on how fat your network pipe is.
Yeah.
And on a gigabit Ethernet, we actually do see the network bandwidth is the bottleneck. On 10 gig, we have not collected all the data, but we believe that on 10 gig, actually all other facts kicks in because you typically won't be able to use all the bandwidth you have. So that's what we have observed.
Is latency plays a part here?
Typically, no. Typically, it's throughput oriented, not latency oriented.
Okay. Because there's work from Berkeley from Kay Afterhout, where she actually says that it's that network is much less than actually some of the stragglers caused because of BSP.
Yeah, that's
BSP is one of the sort of the problems because you have these stragglers until they finish, nothing else can go forward.
Yeah, one of the, as we can see, we show the overhead here. Yeah, the overhead is pretty high. And there is a problem related to communication. There are problems related to aggregation, but I believe a lot of problems are related to synchronization because you need to wait for all the others to complete.
Okay. So, thanks. I've got a follow-up question. So, on the asynchronous model, would these be applicable to many of the algorithms, machine learning algorithms, or are they restricted somehow?
No, I think most of the algorithm actually can use some form of asynchronization, asynchronous training.
Okay. 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 Thank you.
Yeah.
Any other questions?
First, so I know like EM version of the LDA was introduced in 1.3, I believe.
Yeah, I think so.
1.4 introduced the online version, right?
Yeah.
Can you go briefly on like the why it was introduced, like what are the advantages of using online versus EM?
No.
And yeah, that's the first one. The second question was again the why was the so I remember like in a Vertex there was a bipartite graph, right? In the LDA.
Which LDA?
You showed the bipartite graph. Yeah, that one. So the vertex attributes, so if I believe the LDA model works by first you're choosing a topic for each word. Then you sample from the word distribution to choose the word itself, right?
Yes.
And why do you have exactly the number of topics, like size of vector, and which one, like could it be double, could it be integers?
Let me first the first question.
Okay, let's go with the first one.
The EM is actually, there is an implementation of EM-based LDA, and then there is online being introduced, and it's actually using different inference scheme, and again, the EM one and the give something one is actually all based on GraphX.
Okay.
It's kind of a batch-oriented model.
Okay.
And for the online LDA, actually, as I mentioned, first of all, you do not, for those EM and give something, you need to actually go through all the documents in every iteration. And for this one, you actually just need to sample a subset of the documents.
Oh, so for each partition, basically, you're going over only the partition,
Yeah.
like.
You only get a sample of the partition, you do not need to go through the complete partition. So it helps if you have a very large document. And it's also possible to add new documents into it. It's pretty easy to add new documents.
Got it.
So
in terms,
you can do some type of streaming LDA using this scheme.
Got it. Have you done any like benchmark testing in terms of the performance?
We have not compared those two applications, those two implementations. And also, the belief is that even for GraphX-based implementation, the give something hybrid, you probably have better performance in terms of the accuracy and other stuff. And for this one, how it works essentially is you get a distribution of basically get a word topic distribution and a document topic distribution. And then you use that distribution to assign new topics to every word, actually every appearance of the word. After you do that, after you assign new topics to every token, which is every appearance of every word in your document, you really need to aggregate that because, for instance, the word for appears in 3 documents. And these 3 documents can be in 2 different partitions, edge partitions. Sure. After that, after you update that edge partition, you need to aggregate that value to compute the new value for the topic assignment of word for. So this is essentially how you do that, right? You generate new edges, and then you use the edge data to actually aggregate to compute the new vertex data, and then you use the new vertex data to sample the edge. Okay.
So for your sampling, basically, you're updating the edges, rather than the edges.
Yeah.
For all that. One last question. So it seems like the call where you support and the primary service are basically addressing the same problem of having one model in each station that addresses like the repetition.
Okay.
And the first one, like, does that introduce high volume of like coding all of those to like central server? And second one, like, you know, but they're actually mutating on the exactly part that's like how you're gonna go over there. Because now you have global unit. If there's any like the fall packets, you have now the global one only one to like the state code. And how is it gonna work? And first one, like, you know, but the ball codes, you're still gonna have some sort of like a definition of your global server, or not using something.
Well, I think at the concept level, yes, but there are actually a lot of optimization you can do. For instance, on phone network, we're actually doing a lot of cache management on the local host. In that the local host can maintain kind of, you can think of it as sometimes a lot of the implementation actually have a hierarchical structure in that you have a global set of parameter servers. And on each host, on each local host, you have a local copy or a local cache of the parameters, and then a lot of actually happens in a lot of the host communication can happen in local. You only need to synchronize periodically based on the synchronization requirement and so on.
Okay.
And also for the fault tolerance, yes, I mean there are different ways how you can deal with the fault tolerance. For instance, you can do a lot of replication across those between those parameter servers, just like any NoSQL system could do. You can introduce replication. In our case, we are just doing a simple checkpoint in that you just checkpoint to say that to a HDFS, and if anything goes wrong, you just reload that. You can start from a fresh but probably older copy, but you can still make.
Let's talk about like checkpoint for LDA then. You have like your online LDA, right?
Uh-huh.
You have like a giant matrix, and you have like a partition for each of your distribution, and now you have. When you say you're a checkpoint in HDFS, are you loading that matrix into HDFS, like the entire thing?
Yeah, that's what you need to do. You need to load those parameters, which in logistic regression it's the weight, and in LDA it's actually the word topic distribution assignment. You got to that point. Yeah.
I think that was all.
So, when you talked about the broadcast and the problem being that you cannot broadcast more memory, right? I mean, like 800, I've seen 2 gigs of people saying that they want to broadcast 2 gigs of memory across. Why can't you do something where the workers actually know their neighbors, right? They have a map of their neighbors, and from the driver, you basically send to the closest workers the entire broadcast message, and they in turn distribute it to their workers around. But the final checkpoint you basically do to the driver, so that way the work is also distributed amongst the workers. So I've implemented something like that before, but not in this context. And we saw an order difference in the message actually being received by all the workers, because they're sitting idle, they're doing nothing right at that point.
Yeah, actually, the broadcast, there is a BitTorrent type of broadcast implemented in Spark. In that, you actually, just as you mentioned, it's a kind of a peer-to-peer transformation of the data. It's already actually in Spark. And also, for the aggregation, you can do, I mean, there are different ways you can do that. You can do a simple reduce, which essentially means everyone sends data to driver and does the final reduction. But there is also implementation of a tree aggregation in that you have several level of aggregation, and you can do shuffle to other node and doing partial aggregation for you. It's actually implemented in Spark. I didn't show it here for simplicity, but that's actually already getting implemented.
And you still see the bottleneck? You
Yeah.
still see the memory bottleneck?
Yeah, it's still a bottleneck in that, for instance, first of all, everyone needs to still keep a 2 gigabyte copy. And even if you do aggregation, I mean, I mentioned that shuffle is not probably the best performance operation in Spark. You need to go through other disks and the network and so on. It's still a performance hit.
I think in the beginning you talked about a very interesting idea to use low precision instead of double precision. You use flow.
Yes.
But I just wonder, if possible, say initially you just in integer, then when you see convergence of the trend, then or conversion to a certain level, then you ramp up the precision, and in that way you can lower the traffic.
Yeah, that could be done, but on the other hand, actually people are talking about using lower precision than float. For instance, you just want to use some fixed point with some random rounding. So it seems to me that a lot, of course, that what you have described could work, but a lot of the requirement we got is actually they want to use even lower precision, going from float to fixed point, and so my belief is that actually I think they are pretty comfortable with the lower precision, and even want to go even lower.
Yeah. All right. Thank you.
Any other questions? While you guys thinking of few questions, I neglected earlier to introduce one special guest here. Zia Ma, please stand up. She's the Director of Engineering for all open source big data software analytics at Intel. She reported to our Vice President Michael, but Zia runs the show, actual engineering work. So thank you for coming, Zia.
Thank you.
So during the mingling later on, please feel free to reach out to any of us and talk to us. Good. So more questions? We have cookies and coffee after this, but we need a few more questions before we let you have cookies. Come on, Jason came all the way from Shanghai, China to talk to you guys. We're going to take advantage of that opportunity. Good. That's okay. Hopefully, feedback was it informative? Okay. Yeah, okay, there's one more question here first. Go ahead.
So for the parameter server, right, have you thought of using Tachyon?
Yeah, we actually...
Because it's a distributed cache, and you can save whatever you want on it.
We actually have very close, let's put it this way. We actually have worked a lot with the Tachyon. We actually is one of the major contributors to Tachyon. So we actually have a look at the Tachyon and see how we can use that as one of the possible places to put the data in. And this is actually something in progress. We actually have been talking with the guys from MPlab and other on that. We try not to couple the two particular infrastructure because people may or may not have Tachyon. But this is definitely one option we actually can look at. If it's available, we would like to integrate with that.
It can be used?
Yeah, it can be used. It's
very straightforward. It's just save the RGB on it.
Yeah.
Have it distributed.
Yeah.
So, Jason, one question. So, what's the largest sort of cluster size has some of the customers run?
Typically, several hundred. Something like that.
And successfully scaled to pretty...
Yeah, it runs pretty well.
Okay, all right, thank you.
For a single job. I mean, if you look at the larger clusters, they have very large clusters managed by Yang, but a single job typically runs several hundred, 200 or 300.
Actually tested faults in those clusters.
You want to ask?
Yeah.
Oh, he wants to ask something.
So have you actually tested the fault scenarios in that, bringing down clusters and figuring out whether it actually works as designed?
Yeah, it actually recovers. Yeah.
In one of your slides, you are talking about instead of fully aggregating it, you are talking about something when you are trying to say about the improvements. If you can re-clarify that one?
Let's see.
I think it was more aggregating.
Improvements for...
Where you are instead of, not even before that, I think much before that. I cannot see without my slide today.
Let me see.
Yeah, so,
For which algorithm?
in the initial, where instead of going over the entire set fully when you are aggregating, you are talking about some sampling. Probably I will.
Don't remember.
I'll talk offline.
Okay.
It will be easy.
Okay. Let's see.
Yeah.
It's probably easier. Okay.
Any more questions? I guess I got my questions for coffee and cookies now. Really want to thank you so much for coming, and hopefully this is the beginning of many future meetups here in the Bay Area. We welcome you. Earlier, I didn't have a chance to tell you, I showed you a video about Intel software. I know a lot of people know of Intel. Intel is a chip company, computer processor company, but I wanted to really know, probably you already know if you work with Intel, that we have a huge investment in software, not only in big data analytics, but across the software stack. We really have, I don't know, over how many 1,000 employees across worldwide, multiple world sites, and we really dedicate. How many? Close to 10,000 software engineers worldwide at our corporation, all of us dedicated to enable your community, right? I mean, of course, we have selfish interests. We want to make sure all your software innovation work best on Intel architecture, and that's what we, kind of focus on. But really, what we want you to is create that software infrastructure that allow innovation by people like you, to create the next big thing, and hopefully the next big thing will run best on Intel architecture. And that's why we're here for. That's what we do it. We don't have any other interest except to enable you. So hopefully we'll keep in touch, and let's mingle some more with coffee and cookies, and hope to see you soon. Thanks so much.
Thanks, Chris.